Boys and girls, can everyone hear me? You don't chat as much in the chat box anymore, do you? All good. Tom can hear me. Thanks, bud. Nick. All right. Oh, there you are. Hey, Johnny. How you going? All right, I'm going to get started. Did you just record the thing, Gleno? Oh, good. All right, I'm going to do a bit of chatting first tonight. How's everyone's weekend, all right? Forksy there? Yeah. Yeah. All right, I'm going to keep waffling on. I'll probably be about 10, 20 minutes. I hope not too much longer. I'm going to try and get to Nowra next week. It was going to be Monday, but it has to be Tuesday. Sorry, boys and girls. It's going to be Tuesday next week. I want to see some students. I can't make Monday because I'm up here for a meeting. So is that all right, boys and girls? I spoke to Daniel and George. I'm going to come and see you Tuesday next week. What's that? It's 29th or something. Anyway, I'll confirm again at the end of the week. I'm going to Griffith and Wagga mid-November. I'll confirm the date closer. I need to see the Wagga, Griffith students. I've met everyone on Wagga, but I'm going to come down and make sure everyone's all right in Griffith when Frank's back. So is there any Griffith students there, boys and girls? Me and Pat are coming down to say good day. And it's going to be one night at Wagga, then one night at Griffith. So at least I get a chance to meet everyone. And then there's another week coming up where we're going to come down and meet Maria. So I just wanted to wish everyone the best because we're getting to the end of the year. So, which is good. Assessments. Legal. I'm going to close legal tonight. Actually, Glenn, do you mind closing legal for me now? We've left it open over the weekend just for some students to finish off bits and pieces. Send us an email. You got any dramas? I'm still doing the sweeping from behind, just tidying bits and bobs for little painful errors. Oh, Jared's there. Hello, mate. How you doing? To resolve. On-site supervision, we're going to close that in the next week. There's still heaps outstanding, I think. There's like, out of 115, there's like 85 that submit everything and do really well. And there's about 20 or 30 of you sort of hovering around, not doing stuff. That sort of seems to be the number. Every time we look at the submissions, there's about 85 that do it, and there's 115, so there's another 30 odd that aren't doing it, so I don't know. We'll still be hassling you by the end of the year. If not, we just have to give you an NC, so sorry. If you want to withdraw, there's a couple of guys that are withdrawing, and they're just going to come back and do those couple of subjects next year, which is great. It's not going to cost them any money, all right? So, 28th of December, demolitions due. I had a good question about licensing requirements. I'm going to repeat it because I was talking to Aiden about it. He's asked about commercial. So licensing requirements for residential is pretty easy. It's all under the Home Building Act. 28th of October. Demolition legislative requirements for residential will be under the Home Building Act, inclusive of the WHS Act. Commercial, okay, the legislative requirements are going to be under the National Construction Code because it actually states it. Also the WHS Act, and then also it'll be under, for both residential commercial, I suppose, as per the Council Development Control Plan. So it'll be under their requirements as well. So that's what you need to state for those that aren't really clear. I hope that helps. I'm just jumping around. 28th of October. Next week, we're going to open up materials. I'll probably have a chat about that next Monday, I suppose. You might have noticed the progress bars change. Can you have a look on the right-hand side of the screen? We've done it to clear it up a bit better, and actually I didn't even know I could do both of these, so that's probably my bad. It has the assessment requirements. You can see you've probably only got one up. Is that right? Yeah, because we haven't opened the others. So there's 4 of them, right? The learning activity progress bar, we need you to get like over about 90% complete. If you've missed a day here, a day there with attendance choice, that's all right. But these are a requirement as per the assessment. So there's less assessments, but we want all these activities done, you know, like the site establishment quiz or the site establishment mud map. They all need to be done because it's sort of part of your job as a builder. You know, tonight there's going to be the worksheets. So these all need to be done. Mechanical properties, these are part of the assessment. Okay. If you get a couple wrong, like that mechanical properties, if I did it myself, it's really hard. I'd probably get it wrong. I'd have to go research. So I don't want you to stress about it. Adrian's going to have a good chat and teaches it and discuss it, but it's something that you're not going to remember all the time. Okay, so it's an opportunity to research and find out. So bear that in mind for your learning activity progress bar and your assessment progress bar. Alrighty. Builders package. I've added one item and it hasn't worked. So, sorry, I've added two. I put the standards and tolerances. I also added AS6 1084, but I put 0.2 because 0.2's got more to it. It's probably the one that you would use as a builder. Adrian's probably going to talk about it, or Frank next week, a bit more in depth. But with that, I was just looking at it today. I'm thinking, I don't think anyone knows what a building parameter is. Does anyone know what a building parameter is? Can someone tell me in the chat box or talk? A range that you have to work to, like a parameter, yes. So I've got it, I've put it up. If you look at, let me just put this picture that I took a snapshot first. If you just have a look at the screen, so whenever you do anything, you got to make sure you understand the scope of looking in an Australian standards. And I'm just going to give you a quick example. This is for AS 1684, I think it's 4.2. The criteria specified in this standard are specifically for conventional timber frame buildings, applicable to single and two-story construction, built within the limits of those parameters. So that's those clauses within that standard, right? And I'll just give you one instance. You can see for this one, it shows, you know, the sizes of the building, the spans, the parameters. It'll give you, for example, the width. If it's a 17-meter width, that means you'll have to get that engineer design. You can't work it out yourself as per AS 1684. Does that make sense? So we'll be doing that in more depth next week, but you just got to think about the building parameters for whatever document you research. You need to check any of those building parameters because you might be looking for something and the information is completely wrong because your parameters aren't right. And I thought I'd throw that one in there. All right, I've got a couple of things I'm going to show before Adrian takes over. Let me just sort my screen out. And this will be a couple of minutes. We had the staff went and had a visit to Bunnings Frames and Trusses, and I want you to confirm if you can actually see the detail. It's just a different, it's like a little PowerPoint, but it's off through Microsoft. But has anyone actually been to a Bunnings and a Frame and Truss place? Yeah, and I just thought it might be interesting. This would probably be not even 10 minutes, but we wandered around. So this is for the frames that were being built, and those online, I don't think you can hear you can't hear the audio. You can watch this on your own time, but it doesn't matter, okay, because it's just machinery going. So there's no need for audio, so you can just watch the screen, yeah? Righto, so it's just they're stacking their materials, they're getting all the right timbers correct. Then they have their detailed software to determine the sizes. And they use, apologies for that shot there, a linear saw to cut the sizes accordingly from the computer program. Then they'll have a guy who comes in and he actually, can't move that. He actually starts nailing them together. And I've never seen how they nail them together. Like I've been in the trade for a long time. I've never actually saw this. I just thought it was interesting. So watch how they nail these together. All right, so they actually have the noggings cut at those specified sizes and they just nail it together. Like it's amazing how accurate it is. And I haven't seen it done like that. So then they get it on the table and they move it around so they'll finish off with some more detailed work, putting on their bracing components, and then they stack it ready for delivery. All right, that's for the frames. And then I'll open up this. So this is only less than 5 minutes, boys and girls. So same thing, very similar. We'll have the truss. You can see the truss. I'll let you look at this your own time. I'll just put a couple of quick videos up so you can see the truss components. They all get cut to the designated sizes. Here's just a video showing where the machinery is. So you can see it's on the right hand side. It was getting serviced at that time, so there was nothing getting cut up. All right. And then you can see the ancillary items are stored. You can see the assembly where they start putting it together. All right. And I'll just show you when they start joining it up. And then they press. Sorry, I'll go back. When they start nailing off the gang nail plates, you can see the hydraulics where it comes in and just presses it down. Right. They'll have, you can see they've got the big table there for the highlights, so for bigger frames, or sorry, bigger trusses. And I'll just finish off with this one. No, it's not going to work. Anyway, it's the same. You can see it's that picture there where they, oh, no, it's working. Yeah, sorry. So anyway, I thought I'd just put that up there for you. I found that interesting because I've never really been to a frame and truss place, and it just sort of puts it on perspective. The thing was I found interesting was that they were there for an hour. They didn't stop working, those guys. Everyone was just cracking into it, eh? There was no mucking around. They all wore their goggles, you know. So anyway, it was impressive. All right, I'm nearly finished. I've already spoken about the building parameters. Tonight, Adrian's going to get stuck into load paths and primary loads and so forth. The one thing I want to show you is to make you think about it, why we're teaching this, is to understand the requirements for engineers design and you as a builder to make sure every item gets placed. So do you remember the National Park and Wildlife job that I put up for the commercial one? I've taken a snapshot of some design loads. Now, this is in the specification, right? So this is where Adrian's going to be talking tonight about it. You can see it goes into the design. So it talks about the live loads. So in general, for all levels, it's 3 kilopascals. It goes into the wind loads, and you can see that there's a reference to AS 1170. And then it goes into even more depth with any earthquake loads and so forth. But I put that snapshot up so you can understand why we have to talk about it and why certain bracing requirements go in, or why certain depths for a footing or certain sizes of steel go in. And if you actually don't do it, that's where you get yourself caught and get yourself in trouble, because once it's done, as a builder, there's any rectification work or rework, which is a bit of a dirty word, is not good. So, all right, I'm going to hand over now and let Adrian finish off. So thanks for listening, boys and girls. I'll turn off now, Adrian, and give you the screen.
Okay, thanks a lot for that, Brett. That's very interesting, some of the things that you went through there about some of the things that you've done. And some of you guys will have had an opportunity to see how the, just make sure my screen comes up here. We'll have had an opportunity to see how the truss and frame manufacturing places work over the years. And that's real good to understand that, because they're the ones who often build things for you. I actually worked in a truss and frame manufacturing plant as a supervisor, marking out frames as part of my apprenticeship for a little while. We ran out of work on the Central Coast where I was working, so I went and got a job there, and it was a real good period of time. We used to try and plan the frames, wall frames and everything, and picture where they were going to go so that we had everything just fitted together like a Meccano set when they put it out on site. And it was real good. I hit something with my bumper bar one day, and those big 20-ton jacks were real good for straightening and bending pipe. So it was good. Now, the attendance choice is open, so you should all be pretty right with that. I've been catching up on my marking, so guys who have sent me things, thank you very much. Keep that coming. Even right back to did one marking today was for the first unit, so that's great. Keep all that going, and we'll catch up with you with all your work fairly soon. So I'm just going to refresh my page here, and we'll catch up with where Brett finished off. Well, tonight I promised you that you should be able to get some good completions for your completion bars. I'll just make that visible a little bit more. I really like what Brett's done here for you, and he's been able to put up an assessment progress bar, and so they're the four main assessments for this unit. And somebody's jumped on with their microphone on. Do you want to turn your microphone off there? You're good. And then underneath that is the assessment learning activity progress bar. So this is going to be really helpful. This is the main one that you're going to be assessed by, but as Brett said, make sure you get a whole bunch of these done as well. You can see the percentages there, and that's pretty much what you work on. You need to have 100% of these ones, and you need to have quite a good percentage of these ones, which those ones there will prepare you for the main assessments. Have had a few questions about when do the next assessments open up, and so at the moment assessment 1's opened up, but assessment 2, 3 and 4 will be coming a little bit later. So what I'm going to do tonight is give you the opportunity to get a whole heap more of these ones greened off, and also to be able to get a real good basis for us for understanding structures a little bit more, ready for some of the other assessments. So I'm going to open up this site once again that I shared with you, but I just need you to concentrate for a second and probably look at my screen. No matter what you're doing, just have a look at my screen, because this will be a bit confusing for some of you. On tonight's lesson, which is, funnily enough, is S6. We've been going for a couple of weeks, but we only had 2 nights the first week. So on tonight's lesson down here, we've got a 4 words here, which will take us to a toolbox, which gives you real good understanding of how structures works, and a lot of basically it's a lot of the content that we're going to use to develop all of the engineering details for the plan. So if we had to draw up the engineering details for Mr. and Mrs. Smith's plan, we would need to understand the content in here, and also be able to work through with the standards and things so that we can find all the things like the sizes of the footings, the type of concrete, the size steel, the wind bracing and all those sorts of things. So when you come to access these, which I've just opened up for you, if you're using Chrome as your browser, or if you get an error that comes up, then you need to change over to a different browser. And I'll show you how to do that. This is a Chrome browser, and it works pretty good for most things, but when you come to the topic activity, it's going to come up with a little error. So I'm going to show you how to solve that. If you right click, put your mouse over this loads one and right click and just copy the link address, and then go to a different browser, like for example, Internet Explorer, which I'm going to open up here, and I'm just going to paste that into there and push enter. That'll take us to a browser which actually shows the topic activity, which means that you can actually go through and do some of the activities and things. And this is real useful for a couple that we're going to show, because they're kind of a little bit interactive. So I'll just skim back to where we got this information from. There's 4 links there. They're called hyperlinks in the language. It's just sort of a fast way to get to an address, a web address. And the first one we're going to spend a few moments on here is the loads one. And on this, and then we'll spend a bit of time on forces, properties, and then load paths. So I've got my loads one fired up here, and I'm going to spend a little bit of time looking at primary loads, and then we'll look at secondary loads, and then nature of load. So we'll spend a little bit of time looking at that. If we go back to loads, it talks here about a little bit about some of the structural principles, and you'll see fairly quickly it introduces us to Australian Standard 1170. Okay, 1170 deals with loads and things on houses. And you see down the bottom here, if you need more information about units of force, then you're most welcome to go there and have a little bit of a look at that. I'll just right click there and open that in a new tab so that you can see there's a whole heap of definitions there for units of force. In fact, this goes through units of measurement, units of force, and units of pressure. You're going to see some funny words spoken about during this set of units and these structural units, and it's important for you to have an understanding of them. So you can see we always write, for example, kilonewton as a little k, capital N, megapascals as capital M, capital P, little a, and these are international standard ways using the international standard of units for being able to write up these things. Now, we're not expecting you to understand all of this straight away, but you can research that for further information about how that works. You can actually see how kilopascals works and see how those different things works, and that's just a bit of extra information there for you. So I'm going to focus now for a moment on primary loads, and we've talked about these a little bit already. We've talked about a dead load. So the dead load is, for example, a beam and a couple of columns, and that load exerting down onto things. And basically a dead load equals the volume of a member times the unit weight of the materials. Okay, so lots of products, in fact, most products have already been weighed. You can find out most of the properties of products on the safety data sheets or the material safety data sheets. But in the standards, and especially the Australian standards for different, lots of different products, we have this information that's been published for us. So reinforced concrete is generally accepted that it's approximately 24 kilonewtons per cubic metre. Okay, hardwood is often accepted as, for example, 11 kilonewtons per cubic metre. Mild steel, 77 per cubic metre. Okay, so if we know that information, then we're able to look at a beam like that that has measurements on it, and we're able to do this little calculation. So we find out the volume, length times depth times width equals 1.8 cubic metres, and if the kilonewton per cubic metre weight of reinforced concrete is 24, as per our example there, then we're able to work out what the total weight or total kilonewtons of a dead load of that particular beam would be. Fairly straightforward, but just remember you can refer back to this. Now, I've hit the little star button up the top here and added it to my favourite bar, so I can come back to this particular learning resource anytime I need to, because there's a lot of good information here. So hopefully you're all okay with that. Any questions about that at all? Looks like we're mild steel is listed. I've got a question here. Is 77 for mild steel? That's what that's listed as. Now this chart is just an example that's been put on here. The Australian standards actually has all the different materials on them, and so we can see the latest information on there. So I think we're pretty good with that. Brett's put a little post up on here. Brett's put a post up on the chat box there, which you can have a look at. What have we got there? Building materials. So I'm just going to leave that one for now and keep going through this. Now, the next thing we have is live loads. Now, live loads is a different thing again. You can see there's a bunch of different loads that are listed here, and we're going to have a quick look at these. Live loads is something we have to be aware of because live loads depends on what's likely to occur within the building. It's generally accepted that for houses, the live load rating of a house is 1.5 kilopascals, which means that here for houses, it means that it's 1.5 kilonewtons per square metre. So if we know how big the floor is, we know how big the 4 posts, for example, on each corner of that building might need to be. So we're able to work all that sort of stuff out. So if in this particular case, we take the area of the floors, 24 square metres, the live load's 1.5, multiply that out, we come up with 36. And so that's 36 kilonewtons right across that whole area that could be the live load. Of course, on top of that, we've got a dead load as well. which we've got to allow for. And then there'll be other loads and things as well. Wind loads, there could be snow loads, there could be all sorts of different loads depending on the building. Earthquake loads, those sorts of things. So this gives you an example of how live loads are worked out. And look at the different live loads that are here. For an office, it's often accepted that we're dealing with 3 kilonewtons per square metre. Okay. For houses and things here, for parking vehicles, 5 kilonewtons per square metre. This is greater than 2.5 tonne vehicle. Okay, so this is allowing for per square metre. That can be related back to kilograms approximately. Remember that we deal with it. We work on approximately 10 as the factor for kilograms to kilopascals and kilonewtons and things. But that comes back in when you look back at the definitions page that I showed you. So I've spent a little bit of time on dead load, a little bit of time on live load. We definitely have those two things occur on all buildings. A third thing that we have to allow for is wind loads. And no building is immune from wind, but I'm sure you would agree with me that some buildings have less wind than others. An example is I went out to the community garden where I used to live till we shifted into town recently, and we're talking to them, and somebody was saying, boy, it was windy the other day. On Saturday we had a lot of wind in Wagga. Someone else went out to the the cancer thing where you walk around all day and all night. They went there and it was out in a paddock just out of town. They said that was really windy. And I was thinking about in town, it was hardly windy at all. And so depending on where the house is will determine how much load of wind is going to be on the building. And all these sorts of things come into it, so that we have to do a calculation for every single house, which we will do as we go through in these units. So wind loads have become very important in recent years due to the extensive use of lighter materials. And obviously, the lighter we can build them and the more efficient we can build them, then we don't really need to plan for a big, strong wind when it's not going to ever be subjected to a big, strong wind. Then we have a thing like a vortex, which is a whirling movement of air, which can occur and give us a negative pressure on one side of a building. And wind acts on the structure, and we basically work on the fact that the wind is going to act from the left-hand side of the structure in this case, and the right-hand side potentially the same. And if we work on the worst case, that's how we build the building. But the wind is also going to act on this end and the other end of the building. And we work on the worst case scenario, and that's what we'll work on for the building. And we just have to provide enough strength in that building to resist the worst case wind that's likely to occur on that building. Now, it's not really that hard. We just have to look up the charts and follow a flow chart, and which I'll come to in a second. And then you just write down your answers, do your calculations, and bang, that'll give you any one of 6 to 8 different ratings as far as the wind. Then when you go and choose a beam or a strength reinforcement to resist that wind that's going to blow against it, you just make sure that you've used that particular rating that you calculated. Okay, so that pretty much covers that all okay. Then wind loads 2 is coming from a different direction. And then when we come to wind pressure, that's a separate thing that we look at. So when wind flows around a building, it can produce some very high suction pressures. And that's an example of how that can work. And you can see here, these occur mainly at the leading edges. In these areas, the cladding has to be firmly fixed to the structure and the roof has to be firmly held down. The flatter roof, the higher the suction forces, okay, on a roof. And it's more important to make sure the holding down straps are fixed securely. Move your mouse over the house in the different regions so you all can have a bit of a look at this. And I think this is set up so that when we do this, move your mouse over the different regions of the house to find out more information about the effects. And I think there's a little interactive thing there that works. Not quite sure if that's working at the moment, but you can have a little go at that and you'll find out about the different effects of the pressures of the building. That's not actually working, but anyway, that's all good. So here's some of the factors affecting wind loads. Now, I want you to all have a look at the screen for a second, no matter what you're doing. And I want to point out to you 1, 2, 3, 4, 5 things that go into the production of a number, of a letter and a number that enables us to do all of the rest of our structural calculations for the building. So we're after a number. We're after an N1, N2, N3 or N4, or we're after a C1 or 2 predominantly in Australia. And to do that, we need to be able to do some calculations. And this is just an example, and then I'll show you the Australian standard so that you can easily do these calculations and work this out. If you look at the first thing we have to be able to do is find the geographic location in Australia. Now, for all of us here watching this tonight, we're all pretty much in the green area. Some are down here, some are down here, some might be there. If you're anywhere within, say, 100 kilometres, I think it is, of the coast, anywhere from sort of up around probably Coffs Harbour, I think it is, north, all the way around through to Geraldton, around the coast, but not right on the coast. When you get up around this area, then you'd be still nice non-cyclonic. Once you get up around this area, you go into cyclonic, and obviously the wind gets stronger. So you think to yourself, I thought it got real windy down in Hobart, and you have had a cyclone go through Bega or Illawarra or somewhere not that many years ago, wiped out a few houses. Well, you can get freak cyclones and freak winds that come through. Predominantly, this rating is going to be designed for what they call the 1 in 100 wind rating, and that's what the engineers work on. You can have the 101st year wind that comes through. That becomes an insurable event, obviously, and some things you can't necessarily always build for, but this is predominantly what would be used for most structures and things. The first thing we have to find is a geographic location, and we've got to write down what type that is. That's type A, but we're going to find that in a second, where you see where that's written down. The next thing we have to do is we've got to record what type of terrain category. So are we in an area where there's, in this example, greater than or equal to 10 houses per hectare, or house size obstructions, or are we in well-wooded country, or where are we? And we'll come up with a terrain category. For example, TC1, 2, 2.5, 3, or TC3 goes up to another one there. I think there's might be 3.5. I'll show you that in a second. And when you look at the category, we have to choose a terrain category, and we write that down as well. So we write down the geographic location that we've come up for the exact street address of where we are. We write down the terrain category of this exact street address that we've chosen to do our building. We calculate the height of the building. So in other words, we work out how big a building is going to be exposed to the wind and things like that. And we work out then also the shielding. So is it right in one building inside a whole bunch of other buildings, or is it going to be right next to a big open paddock? And we look at the building shape. We look at all those things, and that brings us into being able to calculate the wind loads that are going to occur. Then if you look at this next little interactivity here, you can see how, for example, in this question, it says, what is the wind load, or the wind load rate on the windward side? And if you look at, if we make this play again, not sure if that's actually working all that good. So here's an example of the winds blowing over there, and here's the wind load rates. And so if we've got a wind of 1.5 kilonewtons blowing against that, of a pressure of 1.5 kilonewtons per square metre, and on the roof, and it's a positive, and on the roof it's a positive 0.8 kilonewtons per square metre. We've got a negative here and we've got a negative there. We're able to do the calculations, and we're able to work out what the loading is going to be. And I think it gives us the answers for that there. So you can see this is a little interactive thing, so that we're actually able to work out what the loading is going to be and what the pressure is going to be, and we'll come up with an answer. So what is the wind load on the windward wall? If you pretty much, that's just that seems to be operating real slow there. Pretty much if you go 1.5 plus 0.8 minus 1.5 minus 0.8, you end up with a naught there, as you can see. Actually, no, you won't, because this 1.5 is coming off at a little bit of an angle. So we look at that, and we can work our way through to be able to do the calculations on those ones. This is working real slow here at the moment. We'll try that one. And here's another one here. I'm not actually doing these activities here at the moment, but I'm going to show you on the code. I think some of these activities are quite good to give you an overview, but the code is actually very self-explanatory, and so I want to focus on showing you how that works. I'm just going to go through to load paths as the last thing we talk about. Actually, let's stick to that. I'll go back to the code. So right up the top of your work here, remember you've got all your codes, and you can access your codes quite easily. I've actually got it open. I think it's probably still open here. So I'm gonna search for, it's not still open, so I'll shut that down and get that started again. Here's my codes. Remember, you can access your codes just using your TAFE username and password. If you've forgotten that because you've got it remembered for accessing the Moodle site, you might just need to reactivate that again so you can get your code. If everybody tries to jump on it once, that might slow it down a little bit. But I'm just going to show you 4055, because 4055 is the code, the Australian standard for wind loads on houses and buildings like that. And here it is, you can see it's there. We don't want amendments. We don't want the superseded one. We want the main one. So we'll just view the document. It seems like nothing's happened, remember, but it eventually will happen in most cases. And this code is much the same as all the codes we're going to be dealing with this unit, in that it's written as, I'm just going to download it and put it to my codes. Probably already had it there, but I'll just save it again so that I've got a little bit more interactivity with it. You can see now I've got the bookmarks on the side, just makes it a little bit easier to be able to find my way around. I'll just turn some of those off there so we can just get the overall of it. So pretty much when we look at Australian Standard 4055, it's like most of the Australian standards, and anytime we have to do anything, we just work our way slowly down through the standard. Pretty much all of them have this type of information. There's an introduction at the beginning, tells you a bit about it, what it's for. And you can see this is for housing. It's got the word housing up the top there. And you all know now that the National Constructions Code has housing as 1 and 10. And that's the one that it's set there. There are some limitations which are shown here. So it's not going to be above a certain height. It's not going to be for above a certain width or more than a certain steepness of a roof and things like that. So you just got to remember that type of thing. There are some limitations. And then when you come to we work down, it gives us lots of other standards and things that are referred to. It actually gives us some drawings here of what, and this is basically the geometry showing you the buildings that it relates to. Maximum of 16 metres in this direction, maximum of a certain slope. Then always at the beginning of these standards, there's definitions, because the wording for these things are specifically written so that we can't get confused with what a word means. For example, raking forces, we can see what those things mean. There's a bit of notation which is more for the engineers. That's basically how they work their formulas and things. That normally goes straight over most of our heads. And then when you come down here for section 2, we've got wind loads, and you can see here's the main ones for non-cyclonic areas, 1, 2, 3, 4, 5, we go up to 6. This gives us our serviceability limit state in velocity per second, so that's going to be meters per second. And this is ultimate limit state. So that information there is going to be more for the engineers, those pieces of information. And then we come down to cyclone regions. So there's 1, 2, 3, 4. You can see there's actually 6 here, not 4, sorry. There's 6 there for this one. And then our C is our cyclones. And then right here is the most important information on probably certainly at the beginning of the whole book, because these four parts here is exactly how you fall back into one of these classifications. So as soon as you go to design a beam or a tie down or a bolt or a piece of wall framing or something, it's going to ask you for one of these numbers here, N1 to 6 or C1 to 4. That's what we have. That's the whole purpose of this book. So this is 69 pages here. And if you could bypass those 69 pages, which you actually can, but I'll show you that a bit later. If you could bypass that and just get straight to N1 to 6 or C1 to 4, then that's all you want. But for the purposes of a bit of learning, and so you can become a little bit more educated, you need to follow these 4 steps here. The first one is to be able to determine the geographic wind speed region as defined in figure 2.1. So that's the first thing. You get a piece of pad of paper, you get your house plan and you get your address, and you look in figure 2.1. So we go down here to 2.1. we're looking for figure, remember, not table. We come down to figure 2.1 and there it is there. I'll shrink that down a bit so you can see that's the one I showed you earlier. And that gives you above 30 degrees. You can basically see where we all are there, and anywhere in our area is called region A. So we follow that little part of the chart there, and when we have that, we write that down. So you're going to need to do an assignment later on, and this is what I would recommend you do. All the years I've taught this, just grab that bit there, or particularly this piece here, and put that onto a Word document. Write down the address of the house that you're going to develop the wind rating for, and then when you've gone to your region and you write that down there, you'd write region A, and then you go to your terrain category. And for terrain category, you have to go to clause 2.3. And remember, terrain category is what's likely to happen in the next 5 years. So we'll work through some of these specifically, but when you go to that clause, which I think was 2.3, you just whip down here to 2.3 and you follow what it says to do for 2.3. There it is there. You just follow that through and you'll come up with a reading from there. And the next one says go to clause 2.4, which is a topographic class, and you work your way through there. You've got to take into account the slope of the ground there, hills and things like that. Are you in the top of the hill? Are you halfway up the hill? Are you down the bottom of the hill? And actually, the first question is, what is a hill? Like, is something that's just a little bump in the road a hill, or is it going to be something like the escarpment at Wollongong? So a hill becomes anything that's a slope of greater than 1 in 20. So you have to have a topographic map to be able to do that, and you know all about that now because you're all past the builder setting out a unit. And then you look at the shielding class and the classification, and you can see shielding as, for example, goes anything from full shielding all the way down to no shielding, where you're right next to the Grand Pacific Ocean, building at Thurul right on the water there. And that's an example of how the Australian Standard 4055 works for us to be able to determine our loadings. I'm just going to jump back to this chap here. Oops, which I already had open actually. There we go. So that's an example of how our wind loading works, and we will eventually come up with one of those ratings from N1 to 6 or all the way through to C1 to 4. Now, you don't have to have a full understanding of all this at the moment. We're going to work through with it, but I have just shown you the standard and pretty much how we can take an address and find the terrain from it. We can do a desktop audit and be able to produce a desktop wind rating that'll happen on a house. And then when we go to look for the tie down bolts or the bracing, we can just take all that into account. Any questions about that so far? I'm pretty sure you've got heaps and heaps of questions, especially when you get an assignment. So if we think about that for a second, we've got Mr. and Mrs. Smith's house plan. So you know the length of the building, the slope of the roof, you know the size of everything with the building. You've got a site plan there. If you picked yourself a site somewhere and went to Google Maps and then you turn on the terrain view, you've got yourself the slope. So you're able to do a desktop, come up with the wind rating. And then when we look at the bracing and the tie downs, you're able to come up with all of that and produce parts of the engineer details for the building. And that's what your engineer does, pretty much that. Now, I did say to you there's a quick way to be able to get that. And the Australian Window Manufacturers Association have produced a little slide rule where you can put all that information in and it'll come up with the end rating. But and so there are also calculators and things you can get where you just have to answer the questions and it'll come up with the answers for all of that. So that's that little bit. And the last thing I want to focus on here with loads is load paths. And I just want to show you how load paths, basically we have to really we have to be careful that we take them into account when we build a structure. And I'll give you an example of how that works. So for example, the load path is the path that the highest load on the building is going to take to get all the way down to the dirt and to the ground. And you all have some construction knowledge now. So for example, you should be able to work that all out okay. And I think if I click on this one here, I'm able to demonstrate what the load path could be, for example. So in this particular case, I'll just identify a couple of structural members. We've got a main beam, we've got a column there, we've got a floor slab, and we've got secondary beams. And here's an example of the load path that could occur in a building. So we've got the roof load path flows down through the walls to the foundation. Look how it's flowing down every single stud, every single truss, down through the members of the truss. Okay, down through into the bearers and down into the footing. So that's example of how that works. There's your wall, your floor, and then through to your foundations. And you can see that everything has a load path. And so that's why the nogging is not a structural member, and except that it just keeps the studs apart. But some parts of a building are structural and some parts aren't structural, but it all has a path. And if we have a window, for example, like this case, any loads that occur inside the window will have to be transferred to the sides of the window, the left and the right, and we'll have to have a proper Australian standard approved method of joining everything so that the load path can continue uninterrupted down to the ground. So the second house I bought in Wagga years ago couldn't open the sliding aluminium windows. Has anybody ever had that problem before? And when I eventually pulled a bit of some of the architraves off and had a look, I found that the builder incorrectly had attached the lintel into the wall stud with about a 10mm checkout, and over time that had moved. And what should have been, so the lintel was pushing down on the top of the window. It had squashed the window a bit, and that meant that the window was pretty much, the window mullions were load bearing. So what should have done is it should have followed Australian standards and had the correct loadings run down through there so that it can transfer to the side studs instead of having the weight go down onto the sides, onto the window itself. And it's real important that we get that right. Otherwise, we're going to get callbacks. We're going to get problems with things. We just want the forces and things to work in correctly. So I've covered loads pretty good. I'm just going to copy this link here and pop that back into this address so that I can cover forces. And I've actually got it in here now. So I'm just going to jump over to the forces. And I did spend a little bit of time on this the other day. So I'm not going to spend much time on that other than just quickly have a look. In fact, I'm not even going to go through that quiz there with you because you're going to do that tonight. But if you looked at forces and things, we have to be aware of forces. We talked about that the other night and how forces can occur. Something that I think this is what we're going to focus on here is, here it is. If we have forces that occur at different angles, then the result or the resultant of those forces could be graphically represented by what you can see here with the little activity. I think this is going to happen. Yep. Okay. So basically, this is what an engineer does. If we want to know how we're going to resist a particular force or what the resultant of a couple of different forces operating from different angles are, we can actually draw it to scale on a piece of graph paper like you can see there. And in this particular case, we've got a 4 kilonewton force acting. In this particular case, we're going to have 1 square represents 1 kilonewton, okay? So we keep it to scale, much the same as I showed you how you can draw. We showed you how you can draw your contours and you can put the site plan to scale. So what we're showing you here is that if we have 4 kilonewtons represented by 4 squares here, acting directly downwards, if we grab this 3 kilonewtons acting at an angle of whatever that angle is, running across at that exact length, so that distance there equals 3, whereas this distance down here represents 4. So it's kept to the same scale. And then the result is going to be that our resultant force, and I think I have to actually draw that in. And yeah, that's how I do it. So the resultant force is going to be a line drawn between where the force starts to where it finishes. And if we measure that line, that's 6.8. Let's say, for example, this line down here is 10 or 1 millimeter. So that's 4 millimeters. That's 3 millimeters. This will be 6.8 millimeters. And if each millimeter equals a kilonewton, then or 10 millimeters equals 10 kilonewtons, then we're able to actually measure that line and measure the angle of that, and we know that that's where our bracing needs to be put. So with the force coming against here and the force dropping down there, this being probably dead load, this one here being live load, it doesn't really matter. We need to have enough bracing so that we've got 6.8 kilonewtons of bracing that's acting in that direction so that that building stays stationary. Okay, now this little activity can be multiplied and made harder just by drawing lines however you choose, but you remember earlier I showed you a picture of a building and it had wind blowing this way, wind blowing this way, some sucking out that way, some sucking out that way. You can actually do this system on a bit of graph paper to calculate what the resultant force would be to keep this building nice and stationary and stable. And this is what we do. So remember, this part over here is just drawing on a graph paper to scale, keeping the angles and things accurately so that we're able to actually work out what the resultant force is of those two different direction forces and different size forces are. And this is a way that engineers actually work out, because you look at a house like Mr. and Mrs. Smith's house, and we've got to put some bracing through that house. It's already been done for you probably, but if you had to calculate the bracing for that house, you've got to work out, are we going to use sheet bracing, or are we going to use metal angle bracing, or what sort of bracing are we going to use? And when we remember this type of thing, then we understand how forces work. So can everybody understand how that works? Johnny Bridges has got a YouTube video. I think he's just posted up there for it. A little bit about how that works. I seem to recall having a bit of a look at that one. So that's awesome. This is called graphical solution of forces. Okay, and we have some things here called vectors. We have the size of the force, and remember, all we're doing here is we're drawing a scale drawing of those forces and giving a length of the line to represent the size of the force that's occurring, and then we're able to accurately work out what the resultant would be. That's great. We went straight to that solution there. I do have to spend a moment here talking about, what's this one here? I think I need to spend a couple of moments here talking about these things. So that's the statics. We'd had a look at that. Point load on a beam. Not going to spend any more time on that. Stress and strain. We just have to understand a little bit here about what stress and strain and different types of stress. So there's a couple of things here that actually we looked at that, but I'm just going to spend a tiny bit more time because you've got an activity coming up tonight on that. So stress, like pressure, is a force per unit area. For example, stress is a force per unit area. Okay, so stress is measured in pascals or kilopascals if it's big, or real big's megapascals. You've heard that term before, haven't you? Megapascals for concrete strength, things like that. The most common unit used for structural materials is megapascals. Okay, typically 25 MPa for concrete and things like that. So then there's another term here called strain, and this relates to the term applied to the deformation or change of shape of an object when a load is placed on it. Delicate measuring instruments can do this, okay, like scales or things like that. So in this particular case, we've got a formula that's introduced here, and we've got a formula. I think you're being preserved from most of the hard structural formulas that we used to do in this course years ago. But in this particular case, we have the formula there of strain equals change in length divided by the original length. And that'll give you an answer there. If you go change in length divided by original length, the answer will be strain, the strain, okay? And then for different types of stress, we've talked about this a little bit already, and we've talked about how the fact that we've got lots of different types of stress that can occur on buildings. I'm just going to skim back and see how we're going with the other ones there. I think we've covered, so that's that one. We've covered most of those. Just going to copy this one and bring up the properties one. And you can see properties comes up here on this activity once again. Now, properties deals with materials and what type of, what a material will do under different situations. So we have things like mechanical properties. And this is real interesting because you would recognize that some material is very brittle. Okay, that's what is the property that causes a material to break or snap off without any noticeable lengthening or changing and then other things are very hard, but they're not so much brittle. The term hardness is usually defined as a degree of resistance to indentation or abrasion. If you've ever used an explosive power tool, one of the tests before using an explosive power tool is to get the fastener and scratch it on the material that you're going to, that you're hoping to fire into. And if that fastener bluntens on the end and the material doesn't scratch, then don't fire the fastener into it, because the fastener is probably softer and going to bounce back. But if the fastener scratches the material, then you should be right to go, provided that it meets the other criteria, obviously not brittle and things like that. Malleability is an interesting one, because this means that a material can be hammered or otherwise worked into various shapes. Okay, ductility is the property which enables a material to be drawn out like wire in the direction of its length. Plasticity is the reverse of elasticity. If a material deforms when loaded and does not return to its original shape, when the load is removed, permanent deformation occurs. This is called plastic behavior. Okay, elasticity is almost all solid materials have some degrees of elasticity. A material is said to behave elastically if it deforms while with loading and then returns to its original shape when the loads are removed. You're thinking of mild steel, and that's pretty good, but it gets to a point where it won't return. Okay, think for example of high tensile fencing wire. You can deform that a fair bit and it'll bounce back again. But then you get low tensile wire, which is you just bend that a little bit and it'll stay bent. Okay, and then we have things like toughness, and with toughness, yield point is the point at which a material bends or breaks. Look at that definition that's coming up there. Toughness can be defined as the resistance to fracture of a material by repeated bending or twisting. So some material like light gauge wire that you might use to tie the reinforcing off with, you can bend that into a tight loop and bend it back and forwards 5 or 6 times and that'll snap. Whereas other material will take a long time before it bends. And then the strength of a structural member is the resistance to be able to offer. It is able to offer to the load that will just cause fracture. For example, the resistance that a millimetre squared of section can offer to the load that will just cause fracture. So we've got example there of some of the terms related to mechanical properties. Now, I'm just going to quickly look at property makeup here, and there's an activity there where you can select and drag, and you're going to do that a little bit later actually in the activity tonight. So you've got one that deals with that. And the last one that I'm going to talk about here is the load paths, and we already talked about that actually. So pretty much that's what we talked about back up here with the structural forces, I think it was, where we looked at somewhere there, we looked at load paths, and I'm pretty sure we looked at the load paths. I'll just see if that's the one. Okay, we looked at load paths in with wind pressure and that type of thing. So can you see there that we've got there's 4 things there for you. Now, we've actually got some student notes here, which I'm going to open up to you, and it's a summary of those things. And this is a Word document that you can save on your computer, and it's pretty much got a summary of all those different things that we just spoke about. So, for example, we go through here with loads. One of the main reasons for failure of structural elements in a building is that they are affected by loads and stresses for which they have not been designed. If a building has been designed for a force, then that's all good. It should stay okay, unless something else fails, gets eaten by termites or something like that. But if it's not designed for the force that's going to go on it or the load that's going to go on it, then that's not good. That means we've failed in our preparation and planning. A load can be defined as being a force, pressure, or weight applied to a structural member. Load is measured in units. So, for example, newtons of force, or kilonewtons if it's too large for newtons. Okay, pressure is your pascals, your kilopascals, megapascals. Talks about that there. Then structural design can be approached in 4 stages. Determine the loads acting on the structure. Calculation of the worst possible results of the loads, determining the physical properties of materials, and calculation of the size and shapes of the materials to ensure safe working capabilities. Okay, how are loads applied to a building? Via the actual weight of the building, the weight of the building's contents, the effects of wind loading, or any other loading that might need to be taken into account. And there's just 3 of them right there, not considering snow loads, earthquake loads, and other things like that. Then we've talked a little bit about dead loads, calculating dead loads. It's not that hard to calculate because somebody's already done it for us. And they've given us charts and things like this, which is taken from, I'm pretty sure that's Australian Standard 1170, where it looks at all the different materials. And most of the standards have tables like this where it looks at the materials and gives us the kilonewtons per metre cubed or metre squared or whatever the most appropriate measurement is. Okay, so then we've got the calculation. Just checking your video, your chat back there, so you haven't all gone to sleep, even though some of this can be a little bit boring. So here's an example of calculating the dead load. In this particular example, we've got a beam that's 10 by 0.6 by 0.3. Now you'll notice right there, I just gave you a little tip without alerting you to the fact that could save you a lot of trouble with your calculations. I call those measurements out in meters. That's the little tip. If I said that's 10 by 600 by 300 and you put it in your calculator like that, you're going to get something that's 10 meters by 600 meters by 300 meters. Or if we put that into the calculator as millimeters, so 10,000 millimeters by 600 by 300 millimeters, it's going to give us a massive answer that will be real hard to interpret. So we always want to put our measurements into the calculator in relation to meters. In this particular case, we go 10 times 0.6 times 0.3, and that'll give us a volume of that beam. Okay, and if we know that it's 24 kilonewtons per cubic metre, thanks for that, Kamal. If we know, I'll come to that in a second, actually, good point, Kamal. If we know that we've got 24 kilonewtons per cubic metre, we can multiply it by that 1.8 and we can come up with an answer here. Now, Kamal's brought up a really good point. After total load is calculated, there's a safety factor added. Kamal's from an engineering background, and that's quite right. So often there's already a little bit of a safety factor calculated. And you might recall that I said a lot of these factors like 24 kilonewtons and things like that, once we turn them into pascals by multiplying gravity, we don't usually work on 9.8 as our gravity. We normally work on 10 because that gives us a 0.2 of a clearance there. It's kind of like making things a little bit worse by 0.2. And if we do that and bump things up to their worst case scenario by rounding things up, then we're going to give ourselves just that little bit more clearance. And if you come up with an answer here that might be 0.8, 4, 3, 6, 2, something like that. Well, if let's say, for example, this came up to 0.7, this amount here, it's better for us to bump everything up so that we go right up to go up to the next nearest amount without going ridiculous, because you'll lose all your jobs. You'll have it so over designed. That's probably the complaint of carpenters, isn't it, that everything gets over designed? So we just want to bump it up a little bit, and then the engineer will allow some safety factors and things at the end of it all. So that covers that bit. Live loads, as similarly to dead loads, there's also tables. I'm not sure how they worked all that out, but I guess they set people up like Mythbusters and said, rightio, we've got 4 or 5 people can fit in this room, probably less than one person per square metre, and we can probably fit a table and chair. So you should take this into account if you get a job that says you're going to have a grand piano and you're going to have some other big heavy object like a spa in the corner and something like that. Because if you're building a floor, 1.5 might not be quite enough for a massive grand piano and a spa and all those sorts of things. You could exceed that, and you might have to take that into account. So that's why that sort of information needs to be in there for the engineer to make a decision, an informed decision on it. There's another example there of calculating the loads, much the same as what we just did. And then we look at load paths, and that's pretty straightforward because we went through that activity with you as well. So I'm just going to shut that little bit down. You can find that there, and that's a good example of how you can do the activities that you're going to do in a second. So pretty much I've gone through all the learning stuff for tonight. But what I want to do is open up the activities for you and just quickly have a look at them, so that I'll just actually quickly skim through and show you what you're going to need to do so that you can jump ahead with it yourselves. I'll just jump back here so I can show you the instructions. There's a couple of activities. I said to you, you'll probably get 8 or 9 or maybe 10 little green boxes tonight. So this first one here, let's pump that over to there and just make sure you read the instructions. In this case, it's just complete the quiz. And so in this case, it's just asking you 6 simple questions. Select the most appropriate structural components. So you're going to be looking at, if you start off 1 here, you're basically going to be looking at some of those examples. So drag the term into its position. That's pretty straightforward. You may need to so choose a definition for a particular loading, some of those sorts of things. You might need to, what's the most common unit of measure? That would be a real good place to go back and make sure that you've got that Word document there so that you can answer those ones. I haven't opened this quiz yet. I won't open any of them yet because as soon as I open them, bang, your concentration's gone. And I just want you to listen to me for a couple more seconds, and then I'll probably answer a lot of the questions that you're going to have in a second when you come to these quizzes. So this particular one says complete the quiz again, and I've already been looking at this, so I'll just continue the next preview. This one's got 1 answer. And in this particular case, match the correct terms by the definitions. There's the link that you want, which you can right click and open in a new tab. And it's going to take you to this toolbox, and you should be able to gather the information from there for that one. Actually, I'm going to just upgrade that link so that it takes you straight to the site, which gives you your ductility and your things like that. That's the actual one that we want right there. I think there was one. I'll check that in a second anyway and upgrade that. So that link's probably going to make it hard for you to find that quiz. So I'll jump back and fix that for you in a second. Just be aware of that. Oh, there's 6 here. Oh, and then this next activity, you'll see down here what you need to do is download this worksheet. That'll be available for you in a second. You'll see what that looks like. And when you download that worksheet, you're going to go through and do similar to what we had with that other activity where you had to calculate the live loads for dance floor, dead loads. You're going to get all that information there for those activities on this Word document there, but the figures will be different. The numbers and things will be different so that you're going to quickly complete that yourself. That's quite a good activity there that's going to basically take you through. If you've got this one downloaded, you'll be able to follow through and figure that one out okay. And then you can submit that once you've done it. You can submit it up here into this worksheet. And then that's pretty much it for you. So here we go. I'll open that up. If you've got any questions, just type it into the chat pod. We're here for a little while to help you with all of that. Remember, I'm going to fix this. Looks like that's real slow. Did I show that? I've got to fix this link on this mechanical properties quiz, so we'll fix that in a second so it goes straight there for you. And we'll set up the upload for you. And I think we're right to probably close off the recording now. Thanks, Glenn, unless anybody else has got any questions. So Han said here, did you end up talking about people not putting steel in their concrete footpaths? Oh, very good. Okay. Thank you very much for that, Han. That was one of the activities we were talking about actually. Now my Australian standards is shut down here, so I'm just going to go back up and grab it again. You'll probably find this, but if you jump onto Australian standards and you do a word search there is actually an Australian standard for paths, and that's the one that you follow, because their paths aren't necessarily a structure thing. I think they call it pavements. They are structural from the point of view of driving things on them, but the paths that are beside your house, you'll find there's a spot here that talks about pavements, the Australian standard for pavements. So this one here is sampling and testing of aggregates, bitumen for pavements, residential bitumen for pavements, glass beading, pavements, residential, that's the one I want to look at. So this is 3727, 2016. I don't even think there was an Australian standard for this before this one came out. But if you look at this one, I'm just going to download that so that we can view it a little bit better. get all our bookmarks and things. If you have a look at this one here, we've got things like I said, it's always the same: contents, scope and general, design, materials, general, construction of concrete pavements, construction of segmental and flags, asphalt pavements, bituminous. So ours would be the concrete pavements one. Let's get that big so we can see. Steel reinforcement. You can do a little search through here and have a look. But in fact, this is going to say, make that bigger so you can see. Oh, that's too big. That might do. Reinforcement for concrete pavements shall be steel reinforcing mesh. So that's probably not quite what we want, because we want to know, do we have to put steel in it? I'm gathering that's the question that's being asked there. The recording can stop if you like, Glenn. I'm just doing a pavements bit, but it's a little bit off the topics. You can leave it going if you like. It says here, concrete shall be in accordance with the requirements Australian standard